All right, welcome everyone. We're going to get started. So today we're continuing on talking about exponential growth and decay. And primarily today we're going to be just finishing up the radioactive decay, and we'll actually look at temperature decay as well, an object that's cooling. And then we'll get started on our next learning outcome, which is linear approximations. All right, so we're going to look at this example 4, and we're going to look at radioactive carbon-14, and it has a half-life of about 5,730 years, and we're going to find its decay constant. So we're talking about radioactive decay, so let's write down our exponential decay formula. So what does it say? It says our quantity of radioactive material at time t is equal to the starting, our initial mass, times the exponential part, e raised to the negative lambda times t. And what we want to do here is we want to find its decay constant. So really what we want to figure out is we want to find lambda. All right, so what do we know? So we have a little bit of information here about radioactive carbon-14. We know what its half-life is. So its half-life is 5,730 years. So let's kind of write that out. What does that actually mean? Well, it means if we were to look at the quantity of our radioactive material at time 5,730, how much material we would actually have, the mass of radioactive material after 5,730 years, would be half of whatever we started with. So it would be half times our starting mass, our initial mass, P0. All right, so let's take those two results, those two equations there, and put them together. So we know our mass at time 5,730 is equal to our equation with 5,730 plugged in for t. And it's also equal to 1/2 times our starting mass. So if we set those two values equal to each other, what does this give us? Well, it gives us an equation that we can then use to solve for lambda. And that's what we're trying to find. We're trying to figure out lambda. So we take our exponential decay formula, plug in the time value that we have. We take that other data point that we know, that the mass after 5,730 years is equal to 1/2 our starting mass, set those two values equal to each other, that gives us an equation. Now if we look at this equation, we want to get lambda by itself. So we just start unraveling it, and the first thing we want to do is get that exponential term by itself, the e term by itself, and we divide both sides by P0, and those just cancel off. So if we do that, we get the equation e raised to the negative lambda times 5,730 is equal to 1/2. All right, so we're getting somewhere. Now we want to get rid of that exponential function on the left. We want to get rid of the e. And so the way to cancel off a function is with its inverse function. So the inverse function of e is natural log, so we're going to apply natural log to both sides of this equation. Natural log of 1/2, we'll deal with that in a second. But the natural log of e and the natural log of that exponential, they cancel off. And on the left-hand side, what we're left with is just the term in the exponent, the negative lambda times 5,730. And this should all be equal to natural log of 1/2. Now we can actually simplify that natural log of 1/2 a little bit. using our log properties. So when we have division inside of a log, it gets converted into subtraction. So this goes from natural log 1 minus natural log 2. So the natural log of the top minus the natural log of the bottom. And natural log 1 is just 0. So this simplifies to just negative natural log 2. So if we fill that in, we get negative, and I'll move the 5,730 in front of the lambda, and then we get negative lambda 2 on the right. And when we keep solving, we're going to divide both sides by the coefficient of lambda there. And when we do that, we get lambda is equal to natural log 2 over 5,730. And there's our decay constant. So we now know the decay constant for carbon-14. And we're going to use that in our next discussion. So you may have heard of carbon-14 before. And one of its applications is with radiocarbon dating. So we're going to look at an example related to this. But first, let's describe how this process works. So in the atmosphere, there's carbon-14, which is a radioactive isotope of carbon. And there's also carbon-12, but that's a non-radioactive isotope of carbon. And so both of these exist in the atmosphere. And they exist in a constant ratio with each other. So they're in a constant proportion with each other. And we're going to look at this in the context of living plants. So let's see what happens. Let's say we have a living plant. So it's going to be green here, and we're going to look in the context of a living plant that's undergoing photosynthesis. So the carbon-14, it's radioactive, it's in the atmosphere. The carbon-12 is non-radioactive, but it's also in the atmosphere. And so we have this living plant that's undergoing photosynthesis, so it is taking in that carbon-14. And what happens is that carbon-14, through the photosynthesis process, becomes part of the actual plant material. So that living organism has this radioactive carbon-14 part of its material, part of its matter. Now the carbon-14 that it takes in decays. So the carbon-14 that's already there starts decaying. But because this is a living organism and it's continually going through photosynthesis, it replenishes that carbon-14 that's decaying with new carbon-14. And so what happens over time is that this plant has a constant level of carbon-14. So this plant material, while it's living, has a constant level of carbon-14 in it. The carbon-14 is decaying, but then new carbon-14 comes in from the process of photosynthesis. Now, what happens when this organism dies? So we have this plant, and it's fall, so we'll do some red leaves here. So now the plant material dies. So what happens? Photosynthesis stops. So the carbon-14 that's already there, still there in the plant material, it continues decaying, but now there's no longer new carbon-14 coming in. So that new carbon-14 is no longer coming in, so it's no longer replenishing the carbon-14 in the material. And that's because it's no longer going through photosynthesis. So we have carbon-14 that's decaying, but then no new carbon-14 coming in to replenish it. And so what happens is we have a decreasing level of carbon-14 in this dead plant matter. And so knowing the decay constant for carbon-14, we're able then to determine the time when that plant material stopped living. So what we can do is by measuring the current level of carbon-14 in the remains of this dead plant matter, we can determine when the organism died. And we'll see how to do this in the next example. So that's a rough idea of how carbon-14 works. So let's try it out in example 5 here. So we have a parchment or fragment of a parchment that was discovered, and it has about 80% of the carbon-14 level found today in living matter. So this parchment is made with plant matter, and what we want to do is we want to estimate the age of that parchment. So we want to figure out when that, essentially that piece of paper or parchment was created. And we'll assume that it was created right when the plant material was harvested in order to create the parchment. All right, so what are we trying to figure out here? We're trying to figure out the time t such that the amount of radioactive carbon-14 is equal to 80% or 0.8 of whatever was there initially. So we have this plant matter that was harvested in order to create the parchment. And so that instant when it was harvested, it stopped undergoing photosynthesis. So the carbon-14 level in the plant matter started decaying or started decreasing. And so now we find the parchment, present day we find the parchment, and there's 80% of the initial amount. And we know that because the atmosphere has a constant proportion of carbon-14 to carbon-12. So what we're trying to find in order to estimate the age of this parchment, we want to find the time t such that P of t is equal to 0.8 times the starting mass. So when we look at this, P of t equal to 0.8 times P0, the P of t is the present amount of carbon material or carbon-14. So that's how much carbon-14 is going to be presently in our parchment. And then P0, this was the initial amount. So right when that plant stopped living, this is how much carbon-14 was in the plant material then. So this is our initial amount. And we know it's undergoing radioactive decay. So let's write down our radioactive decay formula. And we also figured out what lambda is for carbon-14. So we know lambda is natural log 2 over 5,730. So we have our exponential growth decay formula, we have our decay constant, And then we also have this data point that the present amount of carbon-14 is equal to 0.8 times the initial mass, P0. So we can use that all to set up an equation. So we know P of T is 0.8 times P0, and then it's also our exponential decay formula here. So we set those two equal, and then this gives us an equation that we can then solve for T. And so very similar process to what we've seen. We want to get the exponential term by itself. So first thing, divide both sides by the number in front of the exponential. So the P0 cancels off in this case. This gives us the equation 0.8 is equal to e raised to the negative lambda times t. Now we want to cancel off that exponential. So just like before, we apply the natural log to both sides. Natural log and e are inverse functions of each other, so they just cancel. And that leaves us with natural log of 0.8 is equal to negative lambda times t. We know what negative lambda is, so we'll fill that in just a second. And we just want to keep solving. We're trying to solve this for t, so we're going to divide both sides by negative lambda. So t is equal to natural log 0.8 divided by negative lambda. And so if we fill in what negative lambda is, we get negative natural log 0.8, put the negative in front there. And then instead of division by lambda, I'm just going to multiply by the reciprocal of lambda. So 5,730 over natural log 2. So there's our t value. And if we were to calculate that out, just to give us some frame of reference here, we could stop there if we were just trying to do this on a homework problem or an exam or something like that. But it helps to kind of give some context. And so let's calculate that out. And we get approximately 1,860. And so that gives us an approximate age for this parchment. And the units here are years. So this parchment is approximately 1,860 years old. And why is the unit years? Well, the half-life was given in years. So when we, back in that previous example, the half-life was 5,730 years. All right, so we can use carbon-14 to kind of date living matter in recent history. All right, so we're going to look at one more application of exponential growth and decay. So we've looked at population growth, we've looked at radioactive decay, we've looked at radiocarbon dating, and there's one more application that we're going to consider, and that's Newton's law of cooling. So what does this law say? It says that the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings, and it's provided that that temperature difference is not too large. So we're going to be talking about, kind of what we're used to in everyday life. You take a drink out of or you pour yourself a hot cup of coffee, you set it down, and it cools down. So we're not going to be looking at extreme temperatures here. So that's where Newton's law of cooling really applies, more of kind of like just the everyday type situations. So there's the verbal description of Newton's law of cooling, but we could actually translate that into a differential equation. And let's see how that works. So first of all, we see this phrase rate of cooling. So as soon as we see that word rate, we think derivative. And that's what we're seeing on the left here. This is our rate of cooling. It's the derivative of our temperature function with respect to time. So that must mean, and let's state it specifically here, capital T is a function of time, and this represents the temperature of our object that's cooling down. At time t. And a lot of times we just kind of use the shorthand, just capital T there in our notation. We also have the surrounding temperature. So we take that, we pour our cup of hot coffee, we set it down, and there's the air temperature. So there's the surrounding air temperature, or maybe we take a hot object and put it in a cold bath of water, it starts cooling down. So we're going to use T sub S as the surrounding temperature. And for this discussion, the surrounding temp, we're going to consider that it's just constant. So constant air temperature, or if we put something into a cold water bath, the water will be held at a constant temperature. All right, so just a little bit of the notation there. Capital T is representing our temperature of the object that's cooling down, so it's a function of time. And then T sub S, capital T sub S, is the temperature of our surroundings. That's kept constant. All right, so we have our rate of cooling, and that's the derivative of the temperature function with respect to time. And Newton's law of cooling says that that rate is proportional. So what it means to be proportional is that there's some constant which we generally call K. It's the constant of proportionality, where the two quantities that are proportional really just differ by a constant multiple. So the rate of cooling is proportional to the temperature difference. And that's what we're seeing on the right here. This is our temperature difference. So we have our hot object that's cooling down, and it's the temperature difference between that object and the surroundings. So the rate of cooling is our derivative. The temperature difference is that T minus T sub S, and they're proportional. So the derivative is equal to a constant times that temperature difference. So we don't know what this function capital T is. It's an unknown function. So that means we have a differential equation here. And we're actually going to see how to solve this using what we know for our exponential growth and decay differential equation. So let's see how this is going to work. We're going to look at how to solve this. So we're going to let, and it's going to be through a change of variables. So we're just going to let the temperature difference, we're going to call it Y. So we're going to let Y of T be the temperature function minus the surrounding air temp, or surrounding temperature, T sub S. And that's just a constant. So when we do the derivative, if we do the derivative of both sides of that, on the left we get dy dt, and then on the right we get dt dt. And the derivative of T sub S, that's a constant, so the derivative is just 0. So if we take these two ingredients and plug them into our differential equation, This gives us the differential equation dy dt is equal to k times y. And that differential equation, that's the first one we looked at when we were talking about exponential growth and decay. And so we saw how to do that. So we converted this to y. So we did a change of variables. That produces a differential equation that we already know the solution to. So we could just solve that differential equation. And what's the solution? Well, it's our usual exponential growth decay formula. So y of 0 times e to the power kt. And so we now know the function for y, so we can just plug that back in and solve for function capital T. So we're going to convert back to our temperature function T of T. And so if we plug that in, we get the temperature function is equal to y of 0 e to the power kt plus our surrounding air temp, or surrounding temperature. And just to see why we get that, we're trying to solve for the capital T function, so just add t sub s to both sides, and we know what y of t is, so fill that in. So this is our temperature formula for an object that's undergoing cooling. And the only thing we want to just mention here is that y of 0 is the initial temperature difference. It's not the initial temperature. So it's the starting difference in the temperature, not the starting temperature of our object. So let's use this in an example. So let's say we have a beverage that's at room temperature, 72 degrees Fahrenheit, and we place this in a refrigerator where the air temperature is 44 degrees Fahrenheit. And we let it sit in there for half an hour, and we measure the temperature of our drink, and it's 61 degrees Fahrenheit. So we're going to use this information to figure out what the temperature function is for our drink. So we want to find the function T of T that describes the temperature of our drink at time T. So let's see what information we have. We have, well, let's start with our formula for the temperature that we just derived. So we said it was y of 0 times e raised to the power kt plus t sub s. T sub s is the surrounding air temperature in this case. And let's figure out what that is. And we see right here that our drink is sitting inside a refrigerator, and the refrigerator is set to 44 degrees Fahrenheit, and it's constant. So that's our surrounding temperature, 44. What else do we need? We need to know y0, and this is our initial temperature difference. So our drink starts at 72 degrees Fahrenheit. That's our starting temperature, but we want the initial difference. So that is going to be 72 minus 44. So the difference between the starting temperature of our object and the surrounding air temperature. And if we do the calculation there, we get 28. So the initial temperature difference is 28 degrees Fahrenheit. All right, so let's fill all that in. Our formula is 28 e to the power kt plus 44. And so the only thing that's left to figure out then, yeah, I was kind of thinking that. I'm like, I don't know. Who keeps their fridge at 44 degrees Fahrenheit? Things are going to spoil. But if we look at that equation, we need to figure out K. We need to figure out K. That's the last thing we need to do. And then then we have our function. All right, so let's use our other data point that we have. So we know that after half an hour, it's cooled down to 61 degrees Fahrenheit. So that's our one other data point. And we're going to use that then to figure out K. So first, let's convert that just into a nice equation. So that says after 1/2 an hour, so T of 0.5, the temperature of our drink is 61 degrees. So let's fill that in, or let's combine that with the temperature formula that we have so far. So we know that T of 0.5, if we use our formula, is 28 e to the k times 0.5. So we're plugging 0.5 in for T, plus 44. And this value should be equal to 61. So what we have now is an equation that we can then solve for K. So we want to get K by itself. So we start by trying to get that exponential term by itself. And when we do that, let's subtract 44 from both sides. So that gives us 28 e to the 0.5 times k is equal to 17. Whoops. Then we want to get the actual exponential piece all by itself. So we're going to divide both sides by 28. So that gives us e raised to the 0.5 times k is equal to 17 over 28. Now, these all kind of, once you get to this point, once you unravel the word problem, actually solving the equation, it feels like a lot of the same steps for all of these. So we want to get rid of the exponential function. So how do we do that? Well, we apply the natural log to both sides. And that's because e and natural log are inverse functions. They cancel out. And this gives us the equation 0.5k is equal to natural log 17 over 28. And then finally, to get k by itself, we divide both sides by 0.5. So we get, what do we get? K is equal to natural log 17 over 28 divided by 0.5. And that gives us, if we put that back into our formula, that gives us a formula for function t, capital T. And I'm probably going to run out of room, so I'll write it on the next part of that. So just keep that in mind. The very last step is we want to plug this back in. Into the function that we have so far. Now, one little thing to note here is we did make a choice about our units for T. So right here, when we set up this data point, we're using 0.5. So this is really telling us that we chose the units for T to be hours. So when we say half an hour, we could have used minutes. So we could have done T of 30. Here we've set our units to hours, so we're using 0.5. So it doesn't matter which one you use, you'll get the same results, when we get to the next section in terms of estimating what the temperature will be at future times. You just have to be consistent. So if you use hours, stick with hours. If you start with minutes, then stick with minutes. So you just have to be consistent in terms of which units you use. So let's try an example, or let's use this function now. So let's write out what our temperature function actually is. It's 28 times e raised to the natural log of 17 over 28. A little more room here. All divided by 0.5. So that's our K value. And then times T. And then we had plus our surrounding air temp, which was 44. So in this part, that's our temperature function with the K value plugged in. And in part 2 here, we want to figure out the temperature after an additional half an hour goes by. So from our initial data point, half an hour went by. Now another half an hour went by. So really what we're trying to figure out is the temperature after 1 hour. So since our units are, we've chosen them to be hours, we're going to evaluate our temperature function at T equals 1. If we had done minutes, then we'd be plugging in 60. So we just need to be consistent. So if we plug 1 in, we end up with 28 e to the natural log 17 over 28 divided by 0.5 times 1 in the exponent there. I won't write the 1. Plus 44. And if we do, just to get some context here, if we get a decimal, this is approximately 54.3 degrees Fahrenheit. So if we had used minutes, we would have gotten the exact same value. You just have to be consistent. So we started with hours, so we kept using hours for our function. All right, so let's use this formula now, this function capital T, to make another prediction. How long it would take our drink to cool down to 50 degrees Fahrenheit. And so to answer this, we're going to set our temperature function equal to 50 and solve for T. So our temperature function is 28 E. And to make it a little bit easier, I'm just going to leave it as K. We know what K is, so once we actually solve for T, I'll plug the K value in. So there's our temperature function. Just keep in mind we know K. And we're going to set this equal to 50. And so this gives us an equation that we can solve for T. And we're just going to go through the motions again. Very similar to what we did before in order to figure out K. So subtract 44 from both sides gives us 28 e to the kt is equal to 6. Divide both sides by 28. And that gives us e to the kt. And let's leave enough room there for, we know we're going to be plugging in or applying our natural log. So leave a little bit of space there. So if we divide both sides by 28, we get that expression. And we want to get t by itself. So to cancel off the e, the exponential, we need to apply the inverse function to both sides. So natural log. Natural log and e cancel. They're inverse functions of each other. And that leaves us with just k times t on the left and natural log 6 divided by 28 on the right. And we want to solve for t, so divide both sides by k. So this gives us t is equal to natural log 6 over 28. And we know what k is, so let's just fill that in. And since k is a fraction, instead of dividing by k, I'll just multiply by k's reciprocal. So k was the reciprocal of k would be 0.5 over natural log 17 over 28. And so that's perfectly fine for t. But just to give us some context here, let's approximate what that is in decimals. So if we were to plug that into our calculator, we would get 1.544. And the units here are hours. So notice we don't really need, the only step we're using our calculator in these calculations is at the very end when we're just to give us a little context to see, what our time here is approximately. But for a homework question or for an exam question, you could leave your answer like this. Just also include units as well, though. So that would have been whatever that is in terms of hours. All right. So that'll do it for exponential growth and decay. We're going to switch gears a little bit. And the next topic we're going to look at is, we've kind of already talked about it. We're just going to put a little bit of a spin on it. So we're going to be looking at the equation of a tangent line. And really the difference here is we're going to use that tangent line to estimate values of our function. And so we're going to call this linear approximations. So our first definition. The linear approximation of some function f at x equals a is given by the formula f of x is approximately equal to f of a plus f prime of a times x minus a. Now, this might look like a whole new formula we have to memorize, but we've seen this before. And we've seen it with the tangent line. So let's just remember the equation of a line is y minus our y coordinate is equal to m times x minus our x coordinate. And for the tangent line at a point, so let's say we have our function y equals f of x in this little example here. And then we have our point that we're interested in, our point of tangency. This was a comma f of a. So how we found our x coordinate, that's just the a value. How we found the y coordinate of our point of tangency, well, we take our x coordinate and we plug it in to the original function. And then how do we get the slope of our tangent line? Well, that's where we take our derivative and plug it in and plug in our x value into the derivative. So this right-hand side of this formula here, this f of a plus f prime of a times x minus a, that's just the right-hand side of our tangent line where we've solved for y. And so in the context of linear approximations, we give that a special name. We call that the linearization. And so that's our second definition here that we see towards the bottom. The linearization of function f at a, we call it L of x. So on our little diagram here, we have our tangent line drawn, but this is also the graph of L of x. So it's really just the tangent line. We're just calling it a special name now. We're calling it the linearization. And so why does this approximation work? Well, for functions that are differentiable, if we look at that point of tangency, so if we were to really zoom in, so there's our point there. If we were to zoom in on that point, what we see is that the actual curve and the actual tangent line are they look very similar. They're almost indistinguishable right around that point of tangency. So the tangent line and the curve are nearly indistinguishable. So right around that point of tangency there, you can't really tell the difference between the tangent line and the actual graph of our function. So the graph of f is approximately the graph of our tangent. And so we say then that our function f of x is approximately equal to this linearization, this function L of x. So L of x is a brand new function, and it's separate from function f of x, but it has the property that f of x is approximately equal to L of x near x equals a. So near x equals a, the function f of x and the function L of x, they're approximately equal to each other. So we're going to talk more about this idea of linear approximations, but let's first just recall how to find the equation of a tangent line. So let's say we have a function 1 plus x over 1 plus e to the x. We want to find the equation of the tangent line at x equals 0. So to do this, we're going to first calculate the derivative. So step one, let's calculate our derivative. We know we're going to need that to figure out the slope. So let's just get that out of the way first. And when we look at this function, it's a fraction. There's x terms on the top, there's x terms on the bottom, so we have to use our quotient rule. So we're applying the quotient rule, so let's write our quotient as a product, top times bottom, and then top times bottom. And then in the middle there, we put a minus sign. In the first copy, we apply the derivative to the first function, and in the second copy, we apply the derivative to the second function. And then we draw our big fraction sign, and we square the original denominator. So that's quotient rule. Now we just clean things up a little bit. So let's finish differentiating. So derivative of 1 plus x is just 1. So I won't write that. So we have the 1 plus e to the x. That's outside the brackets. That still is there. Then we have minus 1 plus x. And then the derivative of 1 plus e to the x is just e to the x. And then this is all over our denominator squared. We don't multiply that denominator out. Now it might be helpful to simplify this down a little bit. So there's a little bit of room we can go, and we can simplify it down to 1 minus x e to the x over 1 plus e to the x all squared. And we won't go any further than that. We'll stop there with the simplifying. All right, so we have our derivative. Now the next step is we want to find our y-coordinate and our ultimately then our slope. So we know our x-coordinate is 0 here. So to find our y-coordinate, we take our x-coordinate and plug it into the original function. So we're going to plug 0 into the original function. And the original function was 1 plus x over 1 plus e to the x. So we get 1 plus 0 over 1 plus e to the 0. And that just simplifies to 1/2. E to the 0 is just 1. So we end up with 1 over 2, 1/2. So that's step 2. We evaluate the original function at our given x value to find the y-coordinate. Then step 3, we want to find the slope. So this is where we take our derivative and plug in our x-coordinate. So we take the derivative and we're going to plug in 0 into it. So when we do that, we get 1 minus 0 times e to the 0 over 1 plus e to the 0 squared. And then simplifying that, we end up with 1/4. So we have our x-coordinate, we have our y-coordinate, now we have our slope. Those are the 3 pieces that we need for our tangent line. And so finally, we use our point slope formula. Y minus our y-coordinate is equal to m times x minus our x-coordinate. And we just plug all the pieces into that to figure out the tangent line. So our y-coordinate is 1/2. Our slope was 1/4. And our x-coordinate was 0. So there's our tangent line. Normally we like to get this into y equals mx plus b format. So if we do that, we get y equals 1/4 x plus 1/2. So there's our tangent line. And so the process for finding linearizations or linear approximations is going to be very similar to all of this. The only difference is just what we call this. So this mx plus b on the right there, we're going to call that our linearization. So let's try that out in example 2. We have the function square root x plus 3. We're interested in the around the point a equals 1. And what we're going to do is we're going to find the linearization of f of x at the given a value. Really what we want to do here is just find the equation of the tangent line in the form mx plus b. So let's go through the routine. Step 1, we want to calculate f prime of x. So here our function is square root x plus 3. We're going to use the general power rule. And it might be helpful to rewrite our function as x plus 3 raised to the 1/2 power. So general power rule says we bring down the 1/2, put it in front, keep what we have inside the parentheses exactly the same, subtract 1 in the exponent to bring us down to negative 1/2, and then we take the terms that are inside the parentheses and multiply by their derivative. So derivative of x plus 3 is just 1, so I won't write that. So our derivative is just 1/2 x plus 3 to the negative 1/2 power. So for our tangent line, we know we need the derivative, so let's just get that calculation done and out of the way first. Now we start figuring out the little pieces. So our x coordinate here is 1. We want to find the y coordinate. So we take our x coordinate, plug it into the original function. So that means we're going to plug 1 into the original function. And when we do that, we get square root 1 plus 3, which is just 2. We also want to find the slope, so that's the next step. We want to find the slope of our tangent line, and this is where the derivative comes in. So we're going to take our x-coordinate, plug it into the derivative. Our x-coordinate is just 1. So when we plug in 1 into what we calculated for our derivative, we get 1/2 1 plus 3 raised to the negative 1/2 power. And if we do the calculation, we end up with 1/4. So we have all of the ingredients now that we need for our tangent line. So let's start with our point slope formula. Y minus our y coordinate is equal to m times x minus our x coordinate. Just the regular point slope formula. Let's fill in all the pieces. So y minus 2 is equal to 1/4 x minus 1. And let's get it into the form mx plus b. And when we do that, we get x over 4 plus 7 over 4. And so what this tells us then is our linearization at a equals 1 is given by the right-hand side of our tangent line, So we call that right-hand side, it's a brand new function. We call it L of x, and it's x over 4 plus 7 over 4. And so if we compare the graph of the linearization with the graph of f of x, so the linearization is just the graph of the tangent line. F of x is this square root looking function here. It's the curve. And so we see that near this point of tangency, near a equals 1, our linear approximation is approximately equal to our function. And you can see that if we look around that point of tangency, it's hard to tell the difference right around a equals 1. It's hard to tell the difference between the actual tangent line and the curve itself. So we say L of x is approximately equal to our function f of x right around that point of tangency. So this gives us another way to think of differentiable functions. If a function's differentiable, we could think of every point along the curve there. If we were to zoom in on it, it would look like it's part of a line segment. And that's what we're seeing in this graph. If we look right around that a value of a equals 1 here, our square root function really is behaving very similar to what just a line would do. Looks very close to it. All right, so we can use these linearizations to approximate different values of our function then. So in this example, continuing on with this example, we're going to use our linearization that we just found to approximate the square root of 3.98. So we're going to use this linearization of L of x to approximate a value of our function here. And in order to do this, there's kind of two steps. First step, we need to determine the x value that we need to plug in to function L of x. So we're going to plug in an x value into L of x, and that's going to give us our approximation of this square root 3.98. So the first step is, well, let's determine what x value we need to plug in. And so let's write down our function f of x. It's square root x plus 3. And what we want is square root 3.98. And let's solve that for x. So we could cancel the square root from both sides. That gives us x plus 3 is equal to 3.98. And then subtract 3 from both sides to get x by itself. And we see x is 0.98. So that's the value we're going to plug into our linearization in order to approximate the square root of 3.98. So that's the second part. We're going to plug that x value into our linearization L of x. So let's do that. We're going to take 0.98, plug it into our function L. When we do that, we get 7 over 4 plus 0.98 over 4. And doing the calculation there is 1.995. Exactly. So the exact value of our linearization is 1.995. So what our linear approximation tells us is that the square root of 3.98 is approximately equal to the value of our linearization at that x value. So it's approximately equal to 1.995. So this idea of linearizations, it allows us to approximate more complicated functions with just the simple equation of a line. All right, let's try it again, this time for square root 4.03. So going through the same steps, we want to determine the x value. So we take our function, square root x plus 3. We set it equal to the value that we want to approximate, square root 4.03, and then solve for x. And we would get 1.03 here if we went through the arithmetic. And then we take that x value, and that's what we plug in to our linearization function. So we plug in. So when we do that, we get 7 over 4 plus 1.03 over 4. And if we do that calculation, we get 2.0125. So that's the exact value of our linearization. But what this is showing is that the square root of 4.03 is approximately equal to 2.0125. So we've used our function value to approximate the square root of 4.03. Let's try another example. So this was with square root x plus 3. In example 3 here, we're going to use a linear approximation to estimate the number 1 divided by 4.002. So we're not given too much information here. It's up to us to figure out the function f of x. It's up to us to figure out an a value. And then once we have those, then we have to go through the process of figuring out the tangent line, the linearization. So if we look at this function, or look at the number that we're trying to estimate, it's 1 divided by a decimal. So that really tells us, it kind of gives us an idea of what we should pick for the function. we're going to let f of x equal 1 over x. Now we want to figure out the a value, where we want to put our tangent line. And so we look at that number that's in the denominator, and it's a decimal. So it's 4.002. And what we can do is just round that to the nearest integer. So we're going to let a equal 4. So the arithmetic we were doing in our expression there was 1 divided by a decimal. So that's why we chose our function to be 1 divided by x. And then to figure out the a value, where we're going to put our tangent line, we just rounded that decimal number to the nearest integer. So a equals 4. So we have our function, we have our a value. Now we can go through and figure out the linearization. So our x-coordinate is 4. And let's figure out f prime while we're at it. We know we're going to need the slope of our tangent line, so we need our derivative. Just rewriting this, it's x raised to the minus 1 power. So this is just basic power rule. And our derivative ends up being negative 1 over x squared. So the x-coordinate we set is 4. The y-coordinate, we just take our x-coordinate and plug it into the original function. So we're going to evaluate our original function at 4, and this is just 1 over 4. Then for our slope, this is where we use our derivative. We're going to plug our x-coordinate into that. So we're going to take x equals 4, plug it into our derivative, and when we do that, we get negative 1 over 16. So we have all 3 pieces now that we need for our tangent line, our x-coordinate, our y-coordinate, and our slope. So we use our point slope formula. Y minus our y-coordinate is equal to m times x minus our x-coordinate. Plug in all the pieces. So y minus 1/4 is equal to negative 1 over 16 times x minus 4. So we've just plugged in all our pieces. And let's just get it into the format y equals mx plus b. And I'll write this as negative 1 over 16 times x plus 1/2. So there's our tangent line in form mx plus b. And that right-hand side, that's our linearization. So L of x is negative 1 over 16x plus 1/2. And so in order to get the approximation, the last step then is to evaluate that linearization at an appropriate x value. So let's figure out the x value. So we take our function, set it equal to the value that we want to approximate, and if we solve that for x, we see that x is 4.002. And then we plug that into our linearization. So when we do that, we get L of 4.002 is equal to negative 1 over 16 times 4.002 plus 1/2. And so if we calculate that, that arithmetic there, we get that this is equal to 0.249875. And so that tells us then that this 1 over 4.002 is approximately equal to 0.249875. And so we used a linear approximation there to estimate that number. All right, so we've done some little examples here with functions that really aren't too difficult. 1 over x and square root x plus 3. Let's talk about where we would, why would we use a linearization in practice? So when we have just some arbitrary function f of x, the ones that we work with in applications a lot of the times are, it's a complicated expression. So what a linearization does is it produces a much simpler expression. It's just the equation of a line. So if we have a really complicated function, but we know it's differentiable, we can just instead look at its linearization, and we have a pretty good approximation then for what that function is doing. If our function has a complicated expression, then it's going to be difficult to evaluate, whereas a linearization is just a line, so it's easy to evaluate. And then if our function is difficult and we're using it inside of some mathematical model, that function is going to significantly complicate that mathematical model, whereas if we were to use its linearization, that hopefully would simplify the mathematical model. And so one place where this is used quite a bit is in a lot of applications for physics. So as an example, there's a mathematical model that describes the motion of a pendulum. So you have an object suspended from a string, and then you just kind of let it bounce back and forth. And so there's actually a differential equation that describes that back and forth motion. And the differential equation is the second derivative of theta plus g divided by L times sine of theta is equal to 0. We're not going to talk too much about it. Just want to give a little example here. But this differential equation, we've talked a little bit about differential equations in the last section. This differential equation does not have a nice solution. So we're never going to get theta, our unknown function, is equal to this, like we were seeing in the last section on exponential decay, where we had p of t is equal to, and here's the actual function. This differential equation doesn't have that. Doesn't have a nice closed form expression. But if we were to say, look at the linearization of sine, so let's simplify this mathematical model down a little bit by looking at the linearization of sine of theta. Turns out, we'll see this in just a second, the linearization is sine of theta is approximately equal to just theta. So just using that linearization gives us a slightly different differential equation, but this one we actually can solve and get a nice expression for what our unknown function would be. So this idea of linearization is used a lot in applications where we have a complicated function or model, and the linearization actually simplifies it down quite a bit to the point where we can actually solve it. And the upshot here, what's really beneficial about L of x is it not only allows us to approximate just a number, but it actually gives us an approximation of the entire function. So it gives us an approximation of the function f of x over an entire interval. So not only are we using a linearization to just plug in values and see, approximate at a decimal, it actually gives us the linearization. It gives us an approximation of the entire function on a range of x values over an entire interval there. All right, so we'll see next time the actual linearization of sine of x. We'll actually go through that process. And then we'll see one other case where linearization is used, and it's with implicitly defined functions. So implicitly defined functions are notoriously difficult to solve for y, but we can use the linearization of y to get a nice little expression that's not too bad. But we'll see that next time. All right, so we'll stop there. Just a reminder, if you're in Thursday recitation, you have your exam. So the Zoom meeting link was sent out this morning. So make sure you join your Zoom meeting link, 5 to 10 minutes beforehand so you can get settled and that you're ready to start the exam right at your scheduled time. All right, we'll stop there. Have a good weekend. Good luck on the exam if you're taking it today. And then we'll see everyone next week for lecture, next week Tuesday.